Hello and welcome to the fifth part of Hexagonal Multi-surface Pattern lesson in Grasshopper. In this session, as before, we will continue from where we left off in the previous part. We allowed our hexagonal pattern to wrap onto itself seamlessly. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. Today, we will move forward and add yet another optional feature that allows additional geometric weaving within the hexagons themselves through their centroids, specifically tries and quads. So that's the script we built so far, and I will remind you, you can go into the description to this video and download it to follow along. So this is our grid, and before we actually tackle the actual topic of weaving the additional constructions within our hexagons, let me tweak a grid a little bit. Now the grid is correct, we will not change its structure, but we want to change its paths. Let me show you. If I'll move it to the right, this is just a temporary visualization. I will use the node called statistics just to quickly visualize the paths and look at the paths themselves. They have a pretty interesting structure. So the first, as you can see, the path consists from two numbers. The first number represents the column. 0, 0, 0 are three collections of points, which forms the hexagons in a column 0. Then the column 1, then the column 2, then the column 3. 0, 1, 2, 3, etc., etc. No problems with them. However, the second number is strange. So the second number represents the actual collection of hexagons within its column. For example, in the first column, the first group of hexagons has a path of 3, not 0. The next is 9. It's this one. The next is 15, right? And for the column 1, we have 6, then 12, then 18, right? Then again, 3, 9, 15, 6, 12, 18, 3, 9, 15, and etc., etc. This is not ideal. Now, first of all, where these numbers come from? Why we have these strange numbers? Well, we have these strange numbers because they are the remnants of our original grid. If you remember, we started this grid by constructing a base, and this base was isotropic orthogonal grid of points, and this grid of points had a very specific structure and very specific paths, which represents the rows and columns. But then we weave the hexagons, we filtered all unnecessary points, we did some modification to that so it will be exactly as we want, and these numbers still still consists with the old values which belong to the points which actually not already there or in the different orientation and different groups. So what we need to do is we need to rename them, basically change the paths, maintaining the same structure, but just change the numbers. So what I want is that every single column will still maintain the same numbers, 0, 1, 2, 3, they're logical linear flow, but these ones are not. I want that every single hexagon count starts with 0. So for the column 0, we will have 0, 1, 2, 0, 1, 2. For the column 1, it will be 0, 1, 2. For column 2, it will be 0, 1, 2, and so on and so forth. So 0, 0, 0, 0, 1, 2, 1, 1, 1, 0, 1, 2, 2, 2, 2, 0, 1, 2. And of course, it's dynamic. If I will increase the amount of points, and as a result, amount of hexagons, these values are supposed to change. They will change right now, but they depends on is it a pointed top or flat top. Right now we're looking at the pointed top example, and of course they supposed to be dynamically changed. So I dynamically supposed to change these numbers. How are we going to do that? Well, let's actually start doing this. So double click here to create a notch to organize things a little bit. I will still need this node, these paths, and the next step will be deconstructing it. So we already used this node before, you know what to expect. It will split the paths, remove all the syntaxes, and give me the numbers. The first element in the list is our columns. The second element in the list is actually our groups of hexagons, right? 0, 0, 0, 0, 3, 9, 15, and so on and so forth. All right. So next step will be to pick but not the elements in question, but actually pick the first ones which are correct. You will understand why pretty quickly. So I will use the list item, plug that in, and here I have them here in a set 0, 0, 0, 1, 1, 1, 2, 2, 2. Once again, the by default index is set to 0. So we'll take the first element in the list for every single branch, right? Next step will be the flattening this. I want to have a one big list of data with no branches, just a simple list. So right click, flatten, and we have ourselves just a list of data. All right. Now we're going to see that it is actually visible here 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, so on and so forth. Fantastic. Now I need to introduce you the two additional nodes, which are very important. They locate under the sets tab into the sets subcategory here, the green ones. They operate on sets, and the first one which we need is this one called create set. What is set? Set in mathematics is a unique list, a list of unique primitive data. In our case, numbers. So if I will plug this into the list, all of these numbers, the proper set, mathematical set, will be only the unique numbers. So only 1, 0, only 1, 1, only 1, 2, only 1, 3, and so on and so forth. So plug that in and look at the set. You're going to see that indeed now it basically removed all the duplicates. It's really similar to extend to delete consecutive. This node, we will talk about that a little bit later, but delete consecutive removes only consecutive numbers. This one creates a set. It doesn't matter where here the 0 can be. Is it here and the 0, or maybe is it here 0? It doesn't matter. It will leave you only 1. Okay, so this is a set of numbers. The next important node which we need is the member index node. This one, extremely powerful. They oftenly used together, not all the time, but often. So what this node does, this node gives you an ability to find a specific member or a list of members from one tree into another tree and give it an index at where they stored. Think about this way. You have like a bag of, I don't know, Lego bricks, right? Like just a lot, like thousands of Lego bricks, different color, different size, so on and so forth. But every single one of them labeled. The first one, the second one, the third, etc., etc. And you have a few Lego bricks in your hand, like I don't know, 3 Lego bricks, and you want to know, or you wanna find these specific elements in your hand in the big bag, right? And you wanna know what indices they are to find them in this kind of big bag. And that's what this member index actually does. The only inconvenient thing here is the inputs. If you look at the title, it's called set, the first one, as if you need to plug the mathematical set into it. But that's not the case. This is the poor description. This is not a set. This is a data, basically your tree, right? So this is actually your big bag. If you plug that here in your big bag, what is your member? The member is your actual elements in the set, and we're gonna plug that right there. So right now you may think, well, what's the point? We have these numbers, then we have the same numbers. We're finding these numbers in this set, which this is the same numbers, right? Well, stay with me here. It's actually quite a beautiful solution. So when we does this, now our node is actually working. We have two outputs, the index and the count. So if I will look at the index, a few very interesting thing happens. Now, first of all, let's look at the numbers themselves. So we have a data tree, and we have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, index, so on and so forth. What are they? Well, they are indices. You see, it's index. They are indices of these values. Oh, sorry, not this one. I will talk about the map in some other lesson. It's really not very representative in this example. So we're looking at the set. So these ones are the indices of these elements in this data tree, in this big one, right? Let's look at this. So the member 0 in this set has indices 0, 1, and 2. This is the 0, this is a 0, this is a 0. What are the indices? 0, 1, and 2. So we effectively found the indices of the 0 in this list. Let's go to the 1. One member in this set has indices 3, 4, and 5. 3, 4, and 5, and so on and so forth. Another really important observation here is that this data tree has branches. It is a branched tree. This one is just a list. This one is just a list, or a single branch, multiple branches. How it's happened? Well, this is the nature of this node. It does this very deliberately. So basically we have the number 0 here, right? And this number 0 represents in free, this number 0 exists in the set 3 times. And all of these indices belong to the one number, and these one belong to the one number, and this is belonging to the number. It groups that together, basically branch them separately, which is an amazing feature of this node, not only of this node, but a few others. So this is a really, really cool property. Why? Because I do not care about these numbers at all. It doesn't matter what they are. I'm only interested in amount of them per branch. How many zeros we have there? 3. How many zeros? 3, and so on and so forth. And because it's grouped that together, they actually constructed me the proper path. So these elements are not important. The actual paths are very important for me. See, right now we have this construction 0, 0, 0, 1, 0, 2, 0, 3, and you're going to see that 0 is up front. We can immediately cancel it. You don't need that. So for right click, simplify, we'll have just a list of numbers. 0, 1, 2, 3, up to 18. Why up to 18? Because we have 18 elements in our member list, and this is exactly the amount of paths, of course, which we have. Well, the biggest value for the column, not the amount of paths, right? So it's not random, of course. Now, if I graft this tree is already grafted, but I mentioned it in the first video that you can graft grafted trees and graft again and graft again and graft again. It will increase the complexity of the path, because in Grasshopper we are not creating nested lists, like list within the list within the list within the list. We will do pretty much the same thing, but through the paths. The path become to be more complex. Additional components add to the path. Now, if I will graft this yet again, you know, and I mentioned it, that in data tree, it is impossible that we have the same branches with the same paths. Value can be the same. Paths of the branches are unique to the data tree. So I can't have 0, 0, 0, 1, 1, 1. It's impossible. It will add complexity. What complexity it will take? You know, we have these 3 elements in the list. This is the first one, the second one, and the third one. When I will graft that, these indices become to be effectively the part of the path. It'll be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0. You get the point. Right click, graft. Look at that. Once again, I don't care about these numbers. I'm caring about the paths. Here they are. And they actually the proper paths. 0, 0, 0, 0, 1, 2, 1, 1, 1, 0, 1, 2, 2, 2, 2, 0, 1, 2, so on and so forth. So the only thing left is to replace the paths. So let's do that. So I will delete these, I will delete these, I will use the node which we used before, replace paths, this one. Now, I hope you remember, data is your data tree. Search, you need to deliberately specify the paths for this tree, and replace, you need to specify the paths for the tree, not the data tree itself, the paths of it. That's the paths. Let's replace. Let's look at the result. Perfect. That is exactly what I wanted. 0, 0, 0. Let me go into the statistics again here and just to visualize. Once again, this is a proper path. 0, 0, 0, 0, 1, 2, 1, 1, 1, 0, 1, 2, x, so on and so forth. Okay, nice. Now, do we have any other options to do so? Like, as with everything in Grasshopper, the answer will be yes. Now we can do it through the series, through the list length, to calculating the list length and operating with these parameters to do the same result, but it will be longer. This one, in my opinion, is a beautiful solution. It's a simple one, it's a quick one, and I believe to some extent elegant one. This is not really specific to this to this case. It's actually a common tactics. Let's put it this way. Right. So now we have. Well, actually, I don't know how how common it is, I don't believe that really a lot of people really use it this way and they go through the series, but a lot of professionals know this approach and they do it this way to change the paths. At least one of the instruments to do so. All right, now when we did that, we actually now can focus on weaving ourselves additional geometry. Now let me visualize what we're gonna do. Now we need an option for triangles and quads. Let's start with triangles. So the triangles basically look something like this, right? So this is the first triangle, right? Inside, then like kind of like the second one here, right? Then the third one here, another one here, right? And another one here, right? So that's what I want to do for all of them, of course, dynamically. Now I want that it will not be just lines, it will be enclosed triangles. They are separate, having its own points, formed and starts from the hexagon or sits within the hexagon, meaning that all of these points basically duplicates multiple times. For example, this is the centroid. How many centroids do I need so that every triangle will have its own point? Well, how many triangles we have? 6. How many points I need? The centroids, 6. What about these points? Well, let's say that this point is A, and this point 0, 1, and 2, and 3, and so on and so forth. So this triangle will be represented by points A, 0, 1. And this one, A1, 1, 2. You're going to see this one was 0, 1, this one was 1, 2. Same point shared, and this one will be shared, and this one will be shared, and this one. We basically need 2 sets of points. One original one and the duplicate of it, but a very specific duplicate. Let's start by duplicating the centroid first. So let me just, oops, no, don't hide anything. Okay, so let me hide this. Let me get my points here. Let me delete this like this. Okay, I will create a notch again, and let's work with the centroid. So the centroid is the first element in the group, right? So this group, the whole group, if you remember, consists from 7 points, 6 for the hexagon and 1 is a centroid, and the centroid is a first point in the list. If you remember, that was our centroid, it was a first point in the group. So that means that I need to pick it. How am I gonna do it? Well, you already know, a list item, this is the first element in the list. Here it is, right? Okay. Now I need to duplicate it. How can I take this point and duplicate it 6 times? A few ways of doing that, but the simplest way is go to the sequence tab in the sets and find these node called duplicate data with 2 rabbits. Now, if I will plug the element into the data and specify the number, how many of them I need? 6. So I will use the item 6 and plug it into the number. I will get myself 6 elements. And by the way, I don't remember, did I mention it or not, but you actually can, let me remove it for now, control click drag. I can actually specify the default value myself. So select on the node, right click, set integer, you can set the default value. I don't advise it though, because it will be difficult to debug. Right now you know that it is in the panel, which means it's hard-coded. You don't need to change it because it's not a slider. It's just hard-coded and you know the value. So I prefer this method and I suggest you to stick with it as well. So now we have 6 elements. So as you're going to see, they're identical. We just duplicated and now we have 6 points. Cool. We solved this part. Now let me actually kind of push it up. The next thing is to work with the points. We need a duplicate of the points, right? What are my points? My points are everything except the centroid. How are we gonna do that? But I need the same grid which I have, but without the point. You already remember, I believe, it is a call index node. We're gonna use a shift list as well, but we'll use it for the different purpose in a second. So call index. Plug that here and you need to specify which one you want to remove from the grid. The first element I want to remove, this is my centroid, right? So let me make it more compact, plug it right there and click. Here we are with no centroid. Cool. Now, Remember what I said, we need duplicates, we need 2 of them. Well, I actually can do it like this, very nice, we have duplicates, but that will not help me. Or it can help me if I will do a pretty dumb solution and manually weave everything. But I would like to go with the node which we already know and make it a little bit more not only interesting but elegant, and we already have the node for that, which is a weave node. If you remember, we use this weave node to connect in the specific order one end of a pattern with the end of the pattern with the beginning of a pattern, and we use a very specific pattern to do that. Now we will use the weave again, but in a slightly different manner. So let me bring it in, weave. I remind you that the pattern by default is 0 and 1, and this is exactly what we want, but let me just duplicate it again so we're going to see what's going on. I'll do it temporarily. So the first pattern is this one, and the second pattern is it really the same? Well, let's think. If I will take this element in the stream 0 and the same one in the stream 1, and I'll be switching 0, 1, 0, 1, 0, 1, so taking from this one, then from this one, then from this one, then from this one, what will I get? Will I get the proper connections? Well, the answer is no, because it will take the same point. It will take this twice, then this twice, then this twice, then this twice, and so on and so forth. I need to have a shift. Take this point, then this point, then this point, then this point, then the same point, then this one, then this one, then this one. How am I going to do it? I will take one of my lists and shift the values to the right on 1. And for that, I will use a very specific node called shift list here in the list subcategory of the sets. So let me just delete this, don't need that. So I will plug my original list, my original data into the list, and by default it shifts set a value of 1, meaning that it shifts values on 1 to the right. Let me show you how it looks. This is our original set of points. Let's look at this section, right? These 6 elements. And this one is the shifted one on 1 to the right, but by default, once again, 1 locally defined value 1. Plug that in here and look at this. You will notice that the order of point changes. What specifically changed? This element goes to the right on 1, and now there are 2 elements. This one was the last one, now this one is the last one. And what was the second one become to be the first one. That's what shift does. You're going to shift on 1, on 2, on million, gazillion, as many as you want. And on top of that, it has additional option, which is called wrap. Now, if I will set the wrap to false, instead of moving it to the back and shifting everything, it just completely removes that from the list. This is a pretty helpful option, but this is a secondary option for the shift list. The main one, of course, is just kind of tossing it, kind of rotating the elements in the list, and you can rotate it clockwise and counterclockwise, so you can add to the back, or vice versa, add back to the front. It will be the negative shift then. Right now we have a positive, and this is exactly what we want. So wrap, we need the same amount of elements. And now if you look at them and you will start weaving, I hope you remember what weaving does. Weaving the pattern, take one element from one tree, then another element from the same element with another tree, then repeats it again, the second element goes, and so on and so forth. So what will happen with this pattern here is that the stream 1 is this one, the stream 0, sorry, is this one, stream 1 is this one. It will take this, then this, right? Then this, right? And so on and so forth. And basically weaving me a collection of points. So instead of 6 points, I will get 12 points. Let's see what it will bring us. So plug this one, look at the weaving pattern here. Right. Now we have 12 points from 0 to 11. But look at the order. 0, 1, 0, 1, 0. You're going to see that it was the first point and the second point, right? Remember that the second list shifted on 1. And we have a duplicate, and the duplicate, and the duplicate, and the duplicate, because these pairs, right, always goes with from this to this, from this to this, from this to this, and so on and so forth. That's why we have these duplicates using a weaving pattern. All right, fantastic. Now, as we have this, we need to kind of like work with this. Right now we have 12 points. We don't need to have 12 points. We need a groups of two. These two, these two, these two, these two, and these two, and these two. How are we going to do it? We need to split that on parts. And every part is supposed to contain only 2 elements because we need 2 for the base of our triangle. How we're going to do it? I will use the specific node here in the sets, in the list subcategory, which called partition list, this one. So I'll plug that in. It asks me for the size of a partition. What is the size of a partition? Well, 2, of course. So 2, remove, let's look at this one, and here we go. Look at that. You see, this is the last point for the first one, and the first point for the second one is the same. Boop. Now we got this one, and so on and so forth. I believe you get the point. So now let me delete this pattern because this is already default pattern. Let me organize it a little bit and weave triangles, right? So okay, well, let's do it this way. So next we need to weave the pattern, but we need to look closer at our data structures. You're gonna see if we want to merge that, and this is the node which we'll be using, merge. I will remind you that the merge command doesn't have data matching built in, does not, meaning that we manually need to adjust our paths because right now they will not merge. These have completely different paths. So I'll take on my data and simplify this. And it is a 0, 0, 0, 1, 1 correct paths. That's great. What's about this one? We did a lot of modifications. Now we have a pretty long path, but a lot of that is rudimental. So simplify. Here they are. We have the free paths right now. And this is the problem. This is okay, but we need to modify it a little bit. This one is the proper one. Why free elements of the path is the proper one? First is the column, second is the hexagon, or basically collection, the third one is actual triangles. This one though has only 2 by default, right? When we simplify that, we removed all the rudimental elements, and we're gonna see that, yeah, that's not final. But look at that, we have 6 elements in the list. What we need to do? Graft it. For everyone, these 2 supposed to be, for these one, these 2 supposed to be, and so on and so forth. How are we gonna do it? Well, very simply, right-click graft, like that. Now we have the same paths, and this point will be related to this one, and this one to this one, and this one to this one, and so on and so forth. Now we can merge. Once again, order matters. So this is the first point that will be the beginning of my triangle. So this is the first one. There, the last one. Let me simplify that a little bit, plug that in, and now we have the proper data structure. Now to prove it, let me go in and construct a polyline, plug that here. Let's say that I would like to close that sub-bool and true, and here we go, we have them. This is 0, 1, 2, 3, 4, 5, 6 triangles within. And I would like to mention it yet again that these, let me go to the polylines, it will be easier. Every triangle here represents by 3 numbers. First one is the column once again. The second is the whole hexagon, you know, the hexagon 0, right? And for the hexagon 0, this one, we have 0, 1, 2, 3, 4, 5, 6 triangles. Here they are, 0, 1, 2, 3, 4, 5, right? So there are no excessive data. All this data is the proper data, the correct one. And before we move on to the just to finally check it, we will use the node which we constructed before. If you remember, we constructed ourselves a cluster. I called it branch slider. Yours probably called differently, and I will plug that in. Let me plug the value, click, let me just kind of hide this one, take this one like this. Right, it's the first one, the second, third, so 0, 1, 2, 3, 4, 5, 6 in total, and then the next one, right? And then the next one, and so on and so forth. Okay, right, nice. Now these out of the way, let's now create the similar construction, but instead of triangles, right, we will do quads. Let's look at the quads for now. How are we going to construct the quads here? Well, they can look something like this. Okay, so this is our quads, right? So 4 points, 0, 1, or like 0, 1, 2, 3, right? 4 points in the list. Now the first question, can we basically do the same, but instead of a shifting of 1, shift on 2 through 1? The answer is no. In this situation, when we go through the point and every next one is the current +1, pattern or the weave will not help us. Let me quickly demonstrate, and so you will understand the differences a little bit better. So I will use just a list of numbers, just separately, not even numbers, let's say strings like letters, A, B, C, D, E, F, right? Right-click, multi-line data. And let's make another one, like a duplicate of it, right? Which will be like A1, B1, C1, D1, E1, and F1, right? So if I will shift one of those, one of those on 1, what will happen is now what was A become to be the last one, B become to be the first one, right? So B, C, D, E, F, A, right? Makes sense? But we need to go through the one, right? So it will be shift 2, right? Just plug that in right there. So it will be C, D, E, F, A, and B1. Makes sense? Well, for now, yes. How about the weaving pattern now? So if I will use the weave again in this situation, let me say that I will have the very specific pattern here. Let me go in line data. It's the default one, this one, and this one. We will have a very specific results. So imagine that A, B, C, D refers to 0, 1, 2, 3, and so on, right? So A is 0 point, B is 1 point, C, and so on and so forth. Now, if you look here, it's definitely not a hexagon. A, C, B. A, C, 1, B. What does it mean? A, C, and then B. So it basically does like this, like roop, will not work. So we, of course, need to go through through additional elements. So if this is the first one, then we need to take this one. So this one, this one, this one, right? So then this one, so this is the first one, second one through this point here, right? So that means that we're gonna increase our pattern. We will take 2 from 0 and then 1 from 1. Does it make sense? Well, let's look at this. A, B, C1. A, B, C1 makes sense. Does it work? Yes, it does. How about the next one? C, D, D1, right? So now we may imagine, of course, that the point here is kind of like out of this example. We're gonna assume this is always the first one, right? So we'll calculate again this one. So that's why A, B, C, it works. It constructs me the proper quad. Now these ones supposed to be constructed, which will be the point, and these ones will be C, D, D1, C. That is correct. C1 and C, same place. C, D, D1 is the same point. Will not work. It doesn't matter what kind of pattern I try to use or what kind of shift I want to break, because the nature of the weave pattern is it will take elements in a sequence, like for example 2 here, 1 here, and then it goes back, and where it left it, it ends here, it goes to the next one, but it don't need to go to the next one, it goes through the one, and I can't do that using the weave pattern. So the weave pattern will not help me. The weave pattern is really good for doing constructions like we did here, to pick a specific order of elements, or when the order is basically 0, 1. When we shift it on 1 and we just like a checkup pattern, quickly take 1, then the next one, then the 1, then the next one, like this, and so on and so forth, right? So this one will not work. What is the alternative? Well, honestly, plenty of alternatives, but I would like to show you. Now, one of the alternatives is the shift list. If we shift the list 3 times, original one, shift it on 1, and then shift it on 2, we can weave them one by one using merge command and construct ourselves the proper quads. But the alternative method will be using the list item command, and let me actually show you how to do that. So just to make things a little bit more convenient, because I actually need to reuse the same stuff over and over again, but it will be a pretty inconvenient node connection, so I'll just duplicate that. So for the hexagons, I basically just create this set again. Let me just do it like so it will be completely separate like this. All right, so this is my centroids for the quads. How many of them I need? 3. That's correct, 3 of them. Here they are. We already know that it works, no problems here. How about this bottom part? Now we of course need to remove the first point from our grid, because we are working with these points right now and only with this one. But instead of working with weave pattern or shifting list and merging, I can literally manually specify what points in what order I want using list item node. That's it. Why? Now you see here that if I'll plug the list item, it will show me the first element in the list, right? And I'm gonna plug my slider and take the third element in the list, the second element in the list, and so on and so forth, right? So, and then I'll just kind of switches between them. But no one prohibits me to place not one element here, one value, but multiple values, right? So I'm gonna say that I would like to have the values, the indices 0 and 1, and plug that in. It'll give me 2, 0 and 1, right? And on top of that, no one prohibits me to take the same element a few times, right? So for example, here we have the element 0 and 1, right? 0 and 1, 0 and 1, 0 and 1. I can say I would like to take 2 zeros. No one forbids me to do that. And because no one forbids me to do that, I indeed can assemble the proper connection myself just through the single panel. So first element, second element, third element, 0, 1, 2, 3, 4, 5. That's their indices. What I need to do to construct the quads, like these one, then these one, then these one. Very simply, this point, this point, this point, which will be 0, 1, 2, then I need to construct this one. Once again, remember, we have this one, this was the first point. Then will be these one, and these one. 2, 3, 4. 4, 5, 0, right? 0, 1, 2, 2, 3, 4, 4, 5, 0. That's it. We already have our collection. The only thing we need to do, split, not split, sorry, split is a different node. We will use it, split list, a different node. Partition list. We will use split list later. So we'll plug that into the list. What is the size of the element we need? I believe we need 3, right? Is it 3 chunks? 0, 1, 2. And now we're gonna go and merge. Basically does the same which you did before. The first point, the second point. Let's create a polyline, plug that in. And it doesn't work, and it doesn't, oh yeah, of course it doesn't work. I forgot. Well, this is a good thing to mention, that you never should be reckless and just speed up. Let's look at this stuff. I forgot to simplify the tree. Right? Now it works. Here they are. Let me actually change the size, but something which we are not planning to change. Remove this. Plug that in like this. All right, That's our proper connection. And on top of that, we actually gonna make additional switch. Let me use the value node, value list, and I'll call it like orientation or something. I don't know how to call it. And this one will be like original orientation, and this one will be shift. Let's call it shift. Yeah. I'm really bad at naming, by the way, but I guess you already understand that. So shift. Now let's create a filter. You already know how it works. We will stream it through the gate, the value 0 and 1. So for the 0, we will take this one. For the 1, we will take a different one. What if I really want to rotate it like 30 degrees? It will be this point, right? So that means it will be not this orientation, not this collection, but it will be 1, 2, 3, 3, 4, 5, 5, 0, 1. Switch. Fantastic. That's it. Let me remove the title for the panel and let me collapse them like this and like this. All right, all right, all right. Let me adjust everything a little bit. Oh, I can of course connect everything because this is the same. This is the duplicate, but probably let it be like this. Whatever. At least it's readable, right? Okay, so before we move on and assemble actually three options, because they, we don't have an additional filter to switch between the solutions. Maybe we don't need any of those. We want a solution without the centroids or without the trees or without the quads, just the hexagons or something else. I would like to mention that these solution, which is picking elements, it actually can be used here as well. No one forces us to use the weave if we don't want to. It's totally legit to just manually construct ourselves a set, or use a shift list, or use a free shift list in this case, like free shift lists here, or use shift lists here and only shift lists and merge, or use the the actual like manually picking the proper elements in the proper order. So once again, there are multiple ways, and there are actually more ways to solving it. I really wanted to show you that weave is actually a pretty powerful node, but it has its limits. I hope you want to understand what these limits are and how to avoid them. Right, now let's actually finalize this part and connect everything together, right? So first of all, let me bring the value list again, value list, and I need to call it somehow yet again. Oh, well, let me type it just geometry, right? Something like this. Very generic shit. So the first one will be, let's say, hex plus centroid. Centroid, right? It will be our first option. The next one will be hex only, like this. It will be 1. The next one will be triangles, and the next one will be quads, right? So this one will be 2 and this one will be 3, like this. All right, now let's bring a filter, stream filter for options. Okay, so let's quickly do it now. I don't need this anymore, so let me delete this. I will select all of these ones probably. can organize this. Well, let's connect it first. So the first one is hex plus centroid. This is already hex plus centroid. So basically this is it. This is our hex plus centroid. Awesome, fantastic. This is hex plus centroid, makes sense. Let me delete this. Right, the next one is hex only. Hex only means that I need to call the first element in the list, right? So plug it here, index 0, remove, right, shrunk, plug, done. And plug it right there. Like this, okay? Now let me switch it to hex only. And let me actually, what's this one? Okay, hex only, hex centroid, right? Works. Okay, what's about the next one will be triangles. Triangles are these ones, and quads are these ones. But if we have so triangles and quads, yeah, that's correct. So if we will switch to trees, we'll have a trees, which we don't see because we don't construct the lines. If it is a quads, it will be a quads, right? We don't see the difference, but it's there. Let's actually visualize. So if it is a triangles, I will go in and I will use call index again, because the first point is a centroid for well, actually I don't need that. Why bother? I just kind of construct a polyline and plug that in, and this is my triangles. So if it is quads, it will be in the form of quads, and if I want, I can switch and shift it from original to the 30-degree rotation. Perfect. All right, now let's switch to hex only and then to hex plus centroid. And for that, as it is a centroid, we actually need a call index here. It will be like this. The first one, call it away, and here we go. Perfect. Okay, so the switch is working. We have all the options which we need. Fantastic. Let me just maybe adjust it a little bit. Let's put this one down instead. All right. Well, before we end this, let's tackle the question which you probably may have. What's about our option to switch the hexagons? Will it change something? Will it break something? Let's go in an example in trees, or even let's go trees. Well, the answer is of course not. So this is our triangles. Let's switch from pointy top to flat top. Perfect. It couldn't break because we did everything correctly here. Here is just a additional kind of divisions, and they're equal, of course. And probably the most interesting result which you can get in 2D, of course, it's when you close the geometry, because it will look like an error. Like, let me show you, bam. But it's not an error. This is exactly how it's supposed to be. It's just the hexagons are elongated. Let me actually increase the division on X like this, right? But it's because centroid is here, but it's supposed to be here. When you wrap around, you will see that it actually constructs the proper construction. And same with quads. Let me plug the quads here. Here are the quads as well, right? And once again, this is the proper connection. It's just really difficult to understand what's going on if you're not thinking about that as an unwrapped or squashed into the unwrapped pattern. And probably if I'll switch it to the pointy top, it will be even interesting, even more interesting. No. Well, actually, no, it's not an error. It's actually exactly how it's supposed to be. And I believe that in the next lesson, when we, finally in the next lesson, we actually start working with surfaces finally. So we actually we almost done in 2D. There will be one additional change here in the beginning, but before we understand the surfaces, it's not logical to add these modifications. So guys, thank you very much for watching. In the next lesson, we will actually start working with the surfaces, and let me just set it up to default settings, for example, hexagons only, and I don't know, is it flat top or pointy top? Doesn't really matter. Let's get pointy top and let's set it open. Okay, that's the where I will left it. All right, guys, thank you very much for watching. Like that. Yeah, thank you very much for watching. See you in the next one.